Right, hello, this is Jishan from JC Tuition. In this video we're going to discuss cell excitability, namely the resting membrane potential and the action potential. So if I were to take a voltmeter and measure the inside compared to the outside, so this can be a reference electrode, this can be an actual electrode measuring the inside, what I'd find is the voltmeter would give a reading of minus 70 millivolts. And this is the resting membrane potential. So we need a potential, quotation marks, as later we'll see that this potential allows our cells to have rapid changes in ions being dragged in from an electrochemical gradient. And this will cause our cells, this voltage will cause our cells to be excited, causing muscles to contract, for example. Sort of like if we were to run a voltage through a light bulb, it would light up. So how do cells set up this resting membrane potential? So the first image, we have a cell with no membrane potential. This cell cannot be excited. The electrolyte composition in our body compartments are as follows, with potassium higher intracellularly inside the cell and sodium ions and chloride ions a bit lower inside the cells compared to the outside. And vice versa, with sodium, the concentration of sodium chloride ions higher on the outside of our cells, but potassium a bit lower. Our membranes are actually more permeable to potassium ions. Why? Because we have these leak channels here. These are leak potassium channels. We also have leak sodium channels here in red. But our cells actually have more leak potassium channels. And because the concentration gradient, so there's a higher concentration of potassium inside the cell than outside, this forms a concentration gradient for potassium to move out down this concentration gradient from the inside of the cell to the outside. And likewise, sodium will be moving into the cell as the concentration gradient is greater outside the cell compared to the inside. But because there are more potassium leak channels, more potassium is pumped outside. So more positively charged potassium ions are charged outwards. Okay? And because these positively charged potassium ions are being pumped out more than the positively charged sodium ions are flowing in, the inside of the cell becomes more negative and we have a membrane potential. The overall net charge inside our cell is more negative. And this just sort of carries on continuing with potassium leaking out through its leak channels passively and sodium leaking in until they sort of reach equilibrium. Our cells want to be in equilibrium. They want the concentration of potassium to be equal on the outside and the inside. So they're going to keep doing this until it's equal. And the same with sodium. They want the same number of sodium ions on the inside. So they're going to keep leaking in until we reach an equilibrium. But because of how I just talked about the inside of the cell being more negative, what this means is there's also an electrochemical gradient trying to pull some of this positive charge back in. So hence there's an electrical force for potassium and sodium ions to move back in because the inside of the cell is more negative. Contributing to this sort of negativity inside the cell are these large impermeable organic anions, such as large proteins inside the cell, and these are sort of also contributing to the negative charge inside the cell. And these impermeable anions are also contributing to the electrical gradient, dragging potassium and sodium ions back into the cell. But overall, the net charge is that the inside of the cell is still more negative. And as these ions sort of reach the equilibrium on both sides of the membranes, potassium outflow starts to slow down and sodium outflow starts to speed up. And the membrane sort of stabilizes around this number, minus 70 millivolts, our resting membrane potential. But after this, our ions are going to try to leak in and out. But this membrane potential is then maintained by the sodium-potassium ATPase pump, which pumps out 3 sodium ions and drags in and pumps in 2 potassium ions. So by doing this, the overall net charge gets maintained at minus 70 millivolts. Equilibrium potential, so that's equilibrium potential, is when the rate of which ions leave the cell due to concentration gradient is equal to the rate at which ions enter the cell again due to the electrochemical gradient. So let's just imagine only one type of cell could cross the cell membrane. Well, that would reach an equilibrium potential, and the equilibrium potential of that ion will equal the resting membrane potential for that cell. And we can calculate the equilibrium potential for a particular ion using the Nernst equation, where EM or VM is the equilibrium potential, Z is the valence of the ion, and this bracket is means concentration of the ion outside the cell, so that's O for outside, and the concentration of the ion inside the cell. And we can just plug the numbers in here and it will give us the equilibrium potential. Let's just consider the equilibrium potential for potassium ions. Well, what's the valency of potassium? Well, if I were to draw its electron configuration, I'm just going to draw the valent electron. It has 19 electrons, so that means it only has one electron in its valence shell. So it's just 1. So 61 divided by 1 is still 1. That's 61 times log base 10. Now the concentration outside the cell is typically about 4, so we know it's quite low on the outside of the cell. And inside the cell it's about 126. So if we plug this into our calculator, we get minus 92 millivolts. So this is quite a good approximation. That is close to our true membrane potential of minus 70 millivolts. The actual measured resting membrane potential is less negative than our approximated one. And that's because we know not only one ion, potassium, moves in and out. We know there's other ions, the sodium and chloride. And we know the sodium in particular leaks inwards. And that positive charge sort of makes the membrane potential less negative. Resting membrane potential of minus 70, so that's where we are here. And now we want to make the cell excite. So what we need to do is run a voltage through it. This rapid change in voltage across the cell membrane, as seen here by the y-axis, is known as the action potential. That's the action potential. And it's due to these sodium and potassium voltage-gated ion channels. So here in stage one, these channels are at rest and all the gates are closed. So as you can see from these images, these activation gates, so these structures here, are shut, not letting any ions sort of pass through. Now, when there is a stimulus, this causes the sodium channels to open up. So positive sodium ions rush into the cell. And we say the cell is now depolarizing. It's going from negative to positive. So stage 2 here is depolarizing. But the potassium channels are still closed. The activation gates are still shut. So now the cell is excited, but we need to get it back to rest, right? So what happens is the inactivation gate, this structure here, actually closes. So now the sodium channel is inactivated. It cannot open. No positive charge can rush in. But the potassium channels now open. So now potassium begins to leave the cell. So positive charge is now leaving the cells. And so we get back towards our negative charge, back towards our membrane potential. This is called repolarization. But these potassium channels here, they stay open for quite a while. And what that causes is more positive charges keep leaving. And actually we go even below this resting membrane potential and we undershoot a bit. Okay? The cell becomes more negative. We'll see why later. And this is called hyperpolarization. We've hyperpolarized the cell, made it a bit too negative. Also in this step, the inactivation gate is now open. The sodium voltage gated channel is no longer inactivated, but the activation gates are shut. So we say the sodium channels have reset. And then the cell makes its way back to its resting membrane potential until the next action potential. Right, so that's the action potential graph shown here. The potential has an all or nothing property, where for an action potential to occur and the cell to excite, we first need a stimulus that is big enough to cause the membrane potential to reach a threshold of about minus 55 millivolts. Okay, so it needs to reach this threshold. So these two stimuli here, down here, well, they cause a slight depolarization, but not enough to reach the threshold. An action potential will not fire. But these two stimuli, well, they do surpass the threshold, and they therefore cause an action potential. And notice how when we reach the threshold, it fires the same sized action potential, positive 30 millivolts. So we either don't reach the threshold, no action potential, or we do reach the threshold and it will provide exactly the same excitability of 30 millivolts. This is the all or nothing property. And this occurs because when we reach the threshold, voltage gated sodium channels, they cause other voltage gated sodium channels to start opening in a positive feedback loop, and it just propagates until we reach the positive 30 millivolts. So we don't want our cells going crazy and producing too many action potentials in quick succession and causing crazy electrical circuits to occur. So our cells can limit this via refractory periods. We have the absolute refractory period shaded here in blue. Here it is impossible for the cell to fire another action potential. Why? Well, remember that the sodium channels are actually inactivated here. So it's impossible to let any sodium channels through. The cell cannot depolarize and fire another action potential. But there's also this relative refractory period here. And here, indeed, it is possible for action potentials to fire if and only if the stimulus is large enough. So in part 1 here, we can see even if we put a larger stimulus in the absolute refractory period, another action potential won't fire. Well, if we do it in the relative refractory period, an action potential does fire. Now here, action potentials can fire because sodium channels have reset, they're no longer inactivated. But we do need a larger stimulus because remember the cell has hyperpolarized due to the voltage gated potassium channels staying open for a bit longer. So we need a larger stimulus to reach the threshold. And the higher the size of the stimulus, the higher the frequency of action potentials fired. Okay? So the strength of the stimulus directly encodes to the frequency of action potentials fired. So cell excitability in the action potential has a lot of relevance clinically, but I thought I would just give one example so this video is not like 4 hours long. So local anesthetics make you go numb at the site of the injection. So for instance, if you ever had a dental procedure, you'll be aware of this. So how local anesthetics work is they bind to your open voltage gated sodium channels and block them, right? And it allows them to also become inactivated and it stabilizes them in this inactivated state. So if they're inactivated, no sodium channels can rush through and depolarize the membrane. The cell cannot excite. So no excitable information is sent by our sensory pathways to our brain, so we do not feel any pain at that site. So thank you for watching this video, and I hope the topic of cell excitability makes a bit more sense to you now. So please visit our website for more fantastic resources. Please also like and subscribe. Goodbye.